A team of researchers built a robot to fold laundry. And while it was working, one of them started messing with it, grabbing shirts from the pile and throwing them back onto the table and even trying to trip it up. The robot just picked each shirt up and tossed it back into the bin. But nobody programmed that, and nobody wrote a line of code saying if a human throws a shirt at you, put it back. The researchers' actual words on camera were, "We didn't know it would do that. Holy crap." A room full of PhDs surprised by their own robot. For 50 years, a robot did exactly what you programmed it to do, and not one thing more. But that just stopped being true. Robots aren't programmed anymore. They are trained on data the same way ChatGPT is. And I'll show you exactly how that works, the whole pipeline, and then answer the question that you probably came here for. Can a software engineer actually get into this? Picture a car factory. Big orange arms welding the same seam 1,000 times an hour, all flawlessly. And they're behind a cage, because if you stand where the weld goes, then that's on you. That arm is a genius at exactly one movement and completely blind to everything else. If you move the car 2 inches, it welds thin air. And that's exactly programmed robotics. A human works out every position ahead of time and writes it down as a set of explicit instructions. That's basically how robotics has worked since 1960s. The reason that it never got smarter is the same reason old school AI stayed dumb. You can't handwrite a rule for every situation the real world throws at you. Think about trying to write fold a t-shirt as a set of step-by-step instructions. You can't. The shirt could be soft, it could be crumpled differently every time, it could begin in 1,000 different positions. The same wall that stopped programmers from hand coding recognize a cat is the wall that kept robotics also trapped in cages. AI only got past that wall in one way. It stopped writing rules and started showing examples. So you don't define a cat, you show the model 1,000,000 cats and it figures out the rest. Robotics just had the same moment about 2 years behind the chatbots. The robot's brain is separated from its body and it became something you train on data instead of programming it by hand. Jensen Huang, whose company happens to sell most of the shovels for this particular gold rush, calls it the ChatGPT moment for robotics. Now, if robots learn from data, you might assume you can just point them at the internet the same way ChatGPT swallowed almost all of human text. But you can't, because there is no internet of robot data. And that's the single thing that makes robotics so hard. ChatGPT had the entire web of text sitting there for free, and image models had billions of captioned photographs. But nobody has uploaded a billion examples showing how exactly joints in a robotic arm should move and to pick up a coffee. As one NVIDIA engineer put it, robots haven't made it to YouTube yet. The data that would teach a machine to act in the physical world almost doesn't exist. And because you can't scrape that data, you have to make it. There are 2 main ways to do that. The first one is to make it by hand, and that is called teleoperation, and it's exactly what it sounds like. A human puppeteers the robot and, try and picture 2 arms wired together. You move the arm in your hands and the robot arm mirrors your movements, and you guide it through the task. Pick up the cup, move it, set it down. Every run gets recorded, and what the camera saw and what every joint did moment by moment. And that paired recording is called one episode. Now do it 50 times or maybe 100 times, and then you have a data set. It's slower and more awkward than it actually looks. One researcher trying it on camera was told to move slowly because the robot arm can actually hurt you. Then comes the training. You take all of these recordings and train it in a neural network called a policy. And a policy is just a fancy name for a function that maps what the robot sees to what the robot should do. It learns to copy the demonstrations, and that is basically imitation learning. The naive version fails in a very interesting way, and tiny errors start piling up. The robot drifts slightly away from the path that it was shown, and then it ends up in a situation that none of its examples covered. And then it falls over. The fix was to stop predicting one tiny twitch at a time and start predicting whole chunks of motion together. And the best version borrows the exact same trick used by image generators. It starts with random noise, then it gradually denoises that noise into one smooth movement. It's basically the same trick that your AI art generator uses, but except now it's aimed at a robot arm. One of these systems learned real kitchen tasks, delicate tasks like opening a cup and slotting in a battery from about 10 minutes of demonstrations. And that surprise on the researchers' faces, the laundry robot tossing that shirt back, that's the kind of emergent behavior you begin getting for free once the system is learning, instead of just following rules. And strangely, a lot of what makes this work is the bad data. That probably sounds backwards. You think it should only show you the robot's perfect demonstrations. But if every demonstration is flawless, the robot never sees a mistake. So the first time it slips, it has absolutely no idea how to even recover. In the words of Sergey Levine, one of the leaders in the field, if you only use good data, that's actually a bad idea. You want the model to see the mistakes and the recoveries as well. The second way to create robot data is to skip reality altogether and use a simulation. If teleoperation is teaching by showing, simulation is teaching by trial and error. The robot tries something, it gets a score, and it tries again. And it gives whatever that pushed the score higher. And that's reinforcement learning. And you usually can't run it in the real world because it needs millions of attempts, and most of those attempts are face plants. Inside a physics simulator, face plants are free. And you don't run just one robot, you run thousands of them at the same time on a single graphics card, and all learning in parallel. A robot dog learned to walk across rough terrain in about 20 minutes this way. An RC car learned to race. And at the beginning of the clip, it's spinning out, but by the end, it's hitting the apex like a professional driver. But simulation has one brutal problem: the sim to real gap. So your simulator never exactly looks like reality. The friction is slightly wrong, the colors seen by the camera are a little different, the weight might be off, and a robot that performs perfectly in a simulation can fall flat on its face in the moment it touches a real floor. The solution is to make the simulation wrong on purpose in 1,000 different ways. Randomize the friction, randomize the lighting, randomize the weight and the sensor delay, the camera position. Train it across all those variations so that the real world becomes just one more version the robot has already seen. OpenAI trained a robotic hand to solve a Rubik's Cube one-handed entirely inside a simulation. Then they transferred the policy onto a real hand. And it worked. The robot's brain is now becoming more and more like the chatbot on your phone. These systems are called visual language action models. You start with a vision language action model, the kind of model that can look like a photograph and talk about what it sees. And it has already been trained on the internet. So it knows what a mug is, it knows what a sink is, and it understands what put the mug in the sink means. Then you attach another component that outputs motor commands instead of words. You swap text tokens for joint angles. Levine again, using an open model as a robot's brain. It's literally the same. The architectures are same, even the weights are the same. A group of students at UPenn got hold of an open model called Pi0. It was released and open sourced by a startup called Physical Intelligence. They loaded it onto their own robotic arm and told it to pick up the pineapple and put it in the basket. And that was a sentence that nobody had trained it on, but it just worked. And one of the students said, "You're simply not used to models working straight out of the box like that." And it worked because the model already knew what a pineapple was. It had learned that from the internet the same way ChatGPT did. It only had to learn the hands. Google's R2 proved this idea a couple of years ago. And now it's everywhere and it's becoming increasingly open. NVIDIA has Groot for humanoid robot. The other models have cleaned kitchens the way they're never seen before. And the recipe is the same one that you already know. Pre-train broadly on everything and then post-train narrowly on your specific robot. And the missing robot data? They work around it as a pyramid. At the top, you have a small amount of precious real teleoperation data. In the middle, a much larger layer of simulated data, and at the bottom is internet video. NVIDIA generated 780,000 training runs, roughly 9 months worth of human demonstrations in just 11 hours entirely inside a simulation. So yes, the brain is real, and that's not just marketing. The capability jumps over the last 2 years are documented and is significant. The body and the final mile though are still brutally difficult. A lot of those jaw-dropping humanoid videos are teleoperated. There's a human wearing a VR headset and controlling the difficult parts off camera. The most home-ready humanoid you can pre-order right now is very upfront about this. It's only 2/3 autonomous, so a human takes over for the rest. Rodney Brooks, who's been building in robots for 40 years, believes teaching to dexterity by watching videos is basically a fantasy. He points out that human hand has around 17,000 touch sensors, and no robotic hand even comes anywhere close. Even the optimists put genuinely reliable robots doing real work in your world at roughly 5 years away. And that's assuming that the data flywheel keeps spinning and not because everyone is waiting for one magical breakthrough. The intelligence is arriving quickly, but the body that it has to live inside is arriving at much slower pace. So, can a software engineer get into robotics? Yes, and it's easier than it has ever been for one specific reason. The most interesting part of robotics has turned it into a machine learning problem, and that is a problem that you already know how to approach. PyTorch, data pipelines, fine-tuning models. So the work has moved off the mechanical engineering bench and onto your laptop, and getting started now costs almost nothing. A research robot that cost $400,000 a decade ago is now equivalent to just a few thousand. And you can buy a real 3D printed training arm for just $120. Hugging Face released an open library called Robot. You teleoperate a cheap arm, record 40 demonstrations, and fine-tune a policy overnight on your computer, and then you watch it run. It's the exact same loop used by $1 billion robotics labs, but just on a much smaller scale. Or you could spend nothing and do the entire thing inside a simulator on your laptop. The NVIDIA engineer teaching this in a public tutorial even says it directly. Use Cursor with Claude to help write the training code. And none of this existed 2 years ago. But robotics is not pure software, and it never will be. The dream job, the one where you only train the robot's brain, is still a small elite club. It's heavy on PhDs and concentrated inside a handful of American and Chinese labs. The robotics jobs that exist in larger numbers still demand the things plenty of people entered software to avoid: C++, real-time control, embedded systems, and hardware that breaks at 2 in the morning for reasons your code cannot see. And for an Indian audience specifically, the robotics industry here is real, but it still leans heavily towards industrial automation and not the humanoid intelligence that research is making headlines. So most of these jobs are not here yet. So test it cheaply, and tonight open a simulator, train one policy to move an object, and then change the friction or move the camera angle and watch the whole thing fall apart. If chasing that failure feels fun, learn some control and C++ next, and you're on your way. And if it doesn't, you've just spent one evening finding that out and not an entire career. If you liked watching this video, subscribe to our channel.